Alright, hell yeah. So a subscriber sent me this problem, and I did it yesterday. I had a Sunday, and I just really cranked on it. The video's 3.5 hours, but I did the wrong problem. Because we're having a projectile, let's say it goes in an arc like this, and it's going to hit two different points, and each point is at a different height. And the distance between those points is going to be 10 meters. I just thought it was this horizontal distance, but it's actually going to be, you know what I mean, the diagonal distance, the actual distance between those. And so Pythagorean's theorem says it's going to be the horizontal distance squared plus the vertical distance squared, square root that. That's going to be the distance. Okay, hell yeah. So I'm going to use a fresh sheet of paper, so let's read through this. A projected particle from the ground passes 2 points, which are at a height h1 and then at h2. h1 is at 12 meters, h2 is at 18. The first part of this problem is like, hey, is it going to be more sensical to have this thing hit both of those on the way up? Let's say it hits h1 at 12 meters and then h2 at 18, and then just continues going up and then going down. The other way we could look at this is it hits h1 at 12 meters and then, you know what I mean, goes through an 18-meter height, but then comes back down at an 18-meter height. So it can pass 18 meters two different places. It can also pass 12 meters two different places, but what you'll see is that you're going to have, whether you take the distance from h2 to be right there in h1, those are going to be symmetric. We can show that in a sec. So you're either going to have h1 here and h2 here, or h1 here and then h2 here, and so we can show that, and that is going to be the solution that gets you the lowest. If your h2 is past 18 meters at the past the top of the arc, the apex, and then back to 18 meters, if that's your h2 and this is your h1 on the way up, that distance being 10 is going to give you the slowest, because that's what it's, the problem says, what could be the minimum speed of that projected object. And the first part of this problem is like, well, do we even need an angle? You know, can't I just show this thing straight up and it's going to go past 12 and it's going to go to 18 and then come right back down? Well, if I did that, and, you know, when I was doing the problem, the 3.5 hour one, that I would say that distance, the horizontal distance, was 0. But now if I'm doing this new problem, I can take that back into consideration where I can project this up, hit 12, hit 18, and then come back down, but the distance between those is only 6 meters. I need the distance between them to be 10 meters, and so the only way to do that is to have this projectile, you know, angled a little bit. So then when I hit 12, let's say I just angle it just a touch, I'm going to hit 12 and then 18 maybe, and maybe just at the top and then come down, and I'm getting a little bit more distance. So maybe instead of 6, now I'm at 8, and so at some point, you know, that angle is going to be to the point where, yeah, it's going to hit through 12, and it's going to hit through 18, and it's going to have a distance of 10 meters. And I'm even going to take a pause here because it seems like you would want to hit both on the way up. But yeah, let me take a quick pause. Alright, I don't want to make this a 3-hour video, but we can, you know, talk about how we can explore this problem, you know, just from a guess and check. Because like one scenario that I want is, you know, I had this scenario where I just go up to 18 and I hit 12 and there's only a distance of 6 meters. Let's say that I always want to just get up to the height of 18 meters. This is 12 meters. And so I'm going to do something like this, and to where, hey, maybe this distance now is 10 meters. You know, so this is only one scenario, you know, where if I have, and even if I, let's see. Alright, hell yeah. So how would we explore this? Well, one is that we're changing the angle. So if I went straight up, I'm going to go to 18, have it stop, and then come back down. if and then so I'm going to have two components here. I'm going to have a velocity component in the y, initial, and then in here I don't have any component in the x. But now I'm going to add in a velocity component in the x direction. And so if I'm trying to always just hit 18, All right, hell yeah. And also, none of my answers are probably correct. All right, hell yeah. I haven't done All right, hell yeah. So now what are we doing? I mean, sometimes I just do this to be like, well, what are we doing? But we do have a quadratic. If this is in the form 0 is equal to ax squared plus bx plus c, I could use the quadratic equation to solve for x. That's going to be negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And I can see that, hey, this is just t, so I'm going to say t is equal to this. Cool. At t1, or I should say at t1 or t2, the only thing that's going to be different is this value for c. So I can say, hey, t1 is just, yada yada y1, and then yada yada y2. So, that part, this value of c is going to be the only thing that changes out of those equations. And we can write it once. Let's write at least we'll write t1 is equal to negative vyi plus or minus the square root of vyi squared minus, now 4a, this is half, so that's 2g, so I have negative 2g so far, and then multiplied by c, which is negative y. There's two negatives, so I'm going to have a positive. So I'm going to have 2g y1. So 2g y1, you can double check that, because that's a hiccup. This negative 4ac is the biggest hiccup in the quadratic. Easiest place to make mistakes. Now we have 2a. 2a is just this twice, so that's just g. Cool. And now we have our... Alright, hell yeah. I had to switch batteries. Okay, so, and this is where we have to say, like, what is this? Okay, this is the time it takes to get to a height of 12, actually, yeah. And so because this has two solutions, this is the time it takes to get to there, or it's the time it takes to get to there. And so now we have to figure out, and this is where, this was like the last thing I did, is to like, hey, let's actually analyze this equation, like just right away. And so g is going to be negative 10. And then so this velocity initial in the y direction, that's just going to be a positive number. I'm going to give it a positive number. And then so this first term, and we can see that this whole thing is just going to be two terms. It's going to be negative vyi divided by g, and then plus or minus the square root of whatever divided by g. Okay, and then so this value is, so we have negative, a positive value, that's positive, and then downstairs we have a negative value. And so overall, this is going to be a positive value. Okay, so let's move on. Underneath here, if this is negative, then we're a non-real solution, so it has no physical. It means that we're not even hitting that location. If this is negative, it would be impossible to hit 12 meters if I threw in, 12 meters right there. So just know that. So this is going to be a positive number. So I'm just going to put this up here. I have plus or minus a positive number up top and then a negative number downstairs. And then we already said that first one was a positive. We determined that. And then so I have, so which is going to make a bigger number and which is going to make a smaller number? So if this is overall a negative, I'm going to have plus a negative. And so I'm going to have two different answers. One's going to be plus a negative, so that's less. If I have 5 plus negative 1, that's 4. Okay, let's say I had 5 minus negative 1. Hey, that's 6. So sweet. So for our first, so for this time 1, if I'm trying to find the time right there, it's going to be the lower one. That's going to be this one. That's going to be the 5 plus. So the t1 that I want is, this number plus the square root divided by g. That's the one I want. Cool. I could do this one, but then I would have to say this is 0.1, and then I might not be interested in this distance, I might be interested in that distance. So it's just a reflection. And so I think that's tip-top. If you, and I'm going to try to do this more, to be like, hey, that's the first thing to do, is like, we know projectiles go up and then they come down, and if it is going to hit two different places because we have a quadratic, one it's going to hit sooner, and then the other it's going to hit later. Both are going to be positive values of time. That should pop out. One is going to be a smaller number, and the other is going to be a bigger number. And so we just went through, I'm just kind of explaining what we went through. We found that if this is the positive root, I get the smaller time. If this was the negative root, I would get the larger time. All right, hell yeah. And then for this problem, we're just, we're using yesterday's knowledge to assume that we want we want to pass 18 meters and we want to get to that location. And so time 2 is going to be the larger value. So let's work through that one. And it's going to be the same. Underneath the square root is a positive. So we're going to have plus or minus a positive divided by a negative. That's the g downstairs. And then the first term is going to be a negative divided by a negative, which is positive. So I'll just throw a big positive here. So we have positive, plus or minus, and this results to be a negative. So we have positive, plus or minus, a negative. And I want the larger time. In both of these, it's going to be a positive time value. And so I want positive minus minus. Because plus, if you have a number and then you add a negative, you're going to reduce that number. So I want to take the number and then subtract a negative. All right, so for t2, I'm going to have this value minus the square root of g. Okay, hell yeah. So now we figured out what roots we want, and now we can kind of figure out, what we're trying to find is just the distance. Like this is x1, and then this is the distance x2. And for most all of these projectile problems, there's going to be no forces in this direction. No wind pushing it, no air resistance slowing it down. It's an ideal situation. The second we impart an initial velocity, it's going to maintain that initial velocity. We can show that with the calculus. We can say the acceleration in the x direction is 0. There is no acceleration due to forces. F equals ma. How we found this acceleration is because our force was the force of gravity. We're going to divide that by mass, and we're going to find the acceleration in the y. And we went through a whole, our first video, we go into gravitational constant, mass of the Earth, divided by the radius of the Earth squared, divided by this mass. The masses cancel, and then this is just g. So the acceleration in the y direction is just that gravitational acceleration. Watch the first video, because we go into that. That's the first hour of that video, exploring that. That's the fundamental of a projectile motion problem. If you don't bring up gravitation, Newton's law of gravitation, then I think you're doing a disservice. If you just instantly say gravity is g, even at a high level, if you're just constantly talking about this term as g, I think you're sidestepping a huge opportunity to not forget about that equation. All right, hell yeah. So now we're going to figure out what we do with these time values. And it should be fairly straightforward. We're going to use Pythagorean's theorem, and we know that this distance is 10 meters. We know this distance is 6 meters, and we just need to know what this distance is. And so let's work on this first one. So the time to get to this first one is going to be this equation. Cool. And let's say we get a value for that. We're going to, let's say it takes 1.5 seconds. That means that we imparted some initial velocity in this direction, and so for 1.5 seconds, this is our speed in that direction. Oh, and I apologize, I didn't finish the calculus on this. So this is the change in velocity in the x direction divided by the change in time. Alright, hell yeah, sorry about that. But yeah, you don't say divided by, but it's the change in velocity with respect to the change in time. That's equal to this, separate variables, and then integrate. So we're going to have velocity in the x as a function of time is going to be, well, there's nothing to in it, so it's just the constant of integration. And so that's going to be, at time is equal to 0, what's the velocity? It's just going to be the initial velocity in the x. This is equal to the derivative of the change in position in the x with respect to time. The solution to this differential equation is based on just easy separation of variables, integrate both sides, and we have x as a function of time is equal to the initial velocity in the x direction multiplied by time plus the constant of integration. So at time is equal to 0. The position is also 0 because we set our datum right there. So hell yeah, that's our equation. So now we can find the position in the x, 1, when time is equal to 1, and that's just going to be Vx, the velocity initial in the x, and then time 1. And so here's our time 1. So I mean, and then it's just simple. If it takes 1.5 seconds and my velocity in that direction is 5, what is that going to be? 7.5. So 1.5 seconds times 5 is, we're going 7.5 meters. Let's say my time to get to here was 1 second, and I'm traveling this way at a speed of 5 meters per second for 1 second. I'm going to go 5 meters. Okay, so that is going to be the distance. Cool. And then the distance, let's say I found time 2. This velocity is still the same, and then if it takes 3 seconds to get here, and I'm going 5 meters a second, now time 2, this is going to be 15 meters. And that's going to be its x position, x2 position. And then so this distance is going to be x2 minus x1. x2 minus x1, where, x2 is going to be Vxi t2, x1 is going to be Vxi t1, and then therefore x2 minus x1. I'm going to skip a step. I'm going to factor out the Vx initial, and we're going to have t2 minus t1. And then so this is going to be that distance. So there you go. So this is the distance I put right here. And then I'm going to just make a simple Pythagorean theorem. I'm going to say, yeah, I'm good. I'm going to say 10, this hypotenuse, is equal to the square root of whatever this is squared plus 6 squared. And then so that's going to be 10 is equal to, this is Vxi t2 minus t1, and we're going to square the whole thing plus 6 squared. So this is my equation that I'm going to use. And then let's just set it equal to 0. So I'm going to have 0 is equal to negative 10, the square root of Vxi squared, t2 minus t1 squared plus 36. Okay, hell yeah. Now, t2 is going to, if I plug in these values, for b and a, so b is going to be Vy initial. And then we have, right here, we have velocity in the x initial. So this is where this is the only point that I put this in. If my velocity in the x, Vx initial, velocity in the y initial, here's my resultant, which is just the velocity initial. And then here's my angle. So I know if I have a velocity in the y and a velocity in the x, I'm going to get an angle. That's how, the velocities add as vectors, and so that determines the angle. So if I put a value for this and a value for that, that gives me an angle. All right, and then so I'm just going to I'm going to say that Vxi, this component is just the hypotenuse. Just know that the component is going to be the bigger number, the hypotenuse. Think of it this way, the bigger number times a percentage, or the bigger number times a fraction of a whole. You know what I mean? And so, and that fraction of a whole is a sine of the angle or cosine of the angle. You just have to figure out which one it is. So I use the put sun shining rays. The sun is shining. This is the sine component. So this is the cosine component. So the Vxi is going to be the hypotenuse, the overall velocity, the magnitude of that. Velocity initial times cosine of the angle. The velocity in the y initial is going to be the overall, just the projected velocity. That's what we're trying to find from this problem. We're trying to minimize this. But this value times the sine of the angle is going to be that Vy initial. Hell yeah. So now I can kind of put it all together. So that's all I did. I mean, that's my solution. I just got this equation and then just did guess and check. I'm sorry, that's all I did. You know what I mean? But it gets you the right answer, and you explore and you learn. So I think, like, I would rather do problems this way, and and then kind of learn the math tricks and be like, okay, yeah, let's throw that into the wheelhouse. But right now, I don't know. I look forward to tomorrow looking at this problem and seeing how they use the math tricks just to get such a simplified answer. And if there is like a no-duh moment, I'll definitely make a video on that, because yeah, you shouldn't be missing out on no-duh moments, especially when it comes to math and math simplification. But we're doing it this way. Alright, hell yeah. So my overall equation is going to be 0 is equal to oh, and I should have a plus here. Sorry about that. But yeah, what's the? I mean, we're basically going back to this. It's just the quadratic equation. We have the distance that we want is 10. I know this distance is 6, and then we found an equation for that distance. Okay, so I'm gonna make this side not equal to 10. I'm gonna get that 10 to the other side. So my equation is minus 10, and in my calculator I just put this as the letter D. And then I'm going to add it to the square root. And so, hell yeah, we can do this. The square root. Cool. And then I'm going to have this squared. So it's Vxi. And again, Vxi is just V initial. I'm going to square it right now. Cosine squared theta. That's Vxi. And now we have... some parentheses. We have T2 minus T1. Okay, so let's go back to that. Because if T2, T2 and T1 both have this negative B, that doesn't change. And so if I have a negative B minus a negative B, sometimes that's hard to see, but let's say I have a 2 minus a 2. Isn't that 0? Let's say I have a negative 2 minus a negative 2. That's also 0, it's just harder to see. Negative 2 plus 2. So if I have a negative b minus a negative b, that's negative b plus b. So when I do this part, T2 minus T1, this part of the equation in both of those just goes away. Cool. T2, we said we wanted to use the negative root, so let's put that. We're going to do... oh, and then all of this, well, we're going to divide everything by g later. If we divide everything by g, I can probably just put the g right here. So I'm just going to do that right now. So everything's divided by g, but now we're just focusing on that top part. So we have a negative square root. So we do have a square root here. And then inside that square root is this. It's a Vyi squared. We said Vyi is just Vi sine theta. So I'm going to do Vi squared and then sine squared theta. Cool. And again, so Vyi squared, I mean, you could just do this. Vi sine theta squared. This is a product of two things, so all we're doing is just squaring one And then this is also the same thing as putting this into parentheses, squaring the other. That's identical to saying sine squared theta. And that's also, like, no one's going to explain that every time. I'm glad I stopped to explain that because I don't know. It's just the way you get used to it, and it feels like you have to be a math genius to actually feel like, yeah, I get it. You're just squaring that portion. You're taking this number, which again, it's a little percentage, between 0 and 1, and then you're squaring it. What does that do? You know, if you have 0.75, square that. You know, if you have if you have 0.866, square that, that becomes 0.75. If you have 0.5, square that, doesn't that become 0.25? All right, so, okay, moving on. But yes, it's also good to know, like, what, this is an equation, it's part of the equation, what does squaring that value, you know, do? Anyway, I think we need to get on, so we have plus 2g, and then we have y1. Well, this is t2, because we're doing t2 minus t1, and this is the negative root we're using, and then so this is y2. Cool. Hell yeah. And then I think I'm done with the square root. Now we're going to add, oh, no. So we're doing t2 minus t1. t2 is a negative. t1 is a positive root, but we're subtracting it. So it's still, I'm subtracting the positive root. So also maybe just good to talk your way through that. So the t1 is going to be the same deal. vi squared sine squared theta. And then we have plus 2gy1. All right, hell yeah. So that was t2 minus t1. We're done with that. It's all divided by g. I could all divided by g. I'm just going to bring that out there. So cool. And this part was multiplying it by. Oh no, I bet I need to actually slow down just a little bit. So we had the Pythagorean theorem said we had 10 squared. I should just have done that first, but 10 squared is equal to 6 squared plus this squared. And so this was this was Vx initial t2 minus t1. And so I already squared the x initial, so that's what this component is. And I can even write that down so I don't make, this was the velocity x initial. This was t2 minus t1 plus this. But I have to square this, so that's interesting. So I have to square the top and square the bottom. So I'm going to square the top. Yeah, so this whole thing, so if I had this squared, well, that's Vxi squared, and then t2 minus t1 squared. And so, yeah, I almost messed that up. And we can kind of see what we have in my calculator. There's the two square roots, subtract. There's the g, and then everything is squared. So that would be g squared, and then all of that squared. Okay, hell yeah. All right, so that was, and then we have plus 36. Because, again, it's just the Pythagorean theorem. We're doing 10 squared on one side is equal to 6 squared plus, this distance squared. That's this equation, and we squared the equation. There's the square of that part, and then there's the square of that part. And then here's the square of 6 meters. Okay, so hell yeah. And so this is all under the square root. I'll just drop it down. That's kind of a bizarre thing to do. But hell yeah. Maybe put ... Hell yeah, so all of that is under the square root. This is outside. So if we look at my equation, I'm going to have negative, I'm going to have negative d, and then added to. This parentheses on the other side is just a parentheses 0.5. That's how the easiest way to do it in the calculator, instead of just doing a the square root sign right now. I'm going to have I'm wondering why there's a negative there, but oh, no, well, yeah. Oh, I see. Maybe I don't see. Oh, maybe we did mess this up, because that negative probably shouldn't be there. Alright, I actually have to go look at this and see if we did make a hiccup. I know we didn't because we checked it with this equation, so yeah, let's roll with it. Is that I'm going to have, on this side, I'm going to have this squared. So we have Vxi squared. Oh, I see. This parentheses has the squared on the other side. And so, yep. And I just don't know if that negative should be there. I think this negative shouldn't be there, and then the negative should be right there. I'm rearranged this equation to do a different problem. So yeah, so hopefully this is what we want, because we want a negative there, and then we want another negative there. And then we have our square, and then we have our 0.5. Okay, hell yeah, and I think this should work out. And we'll see if it does. Okay, so now my method to find, now that we're going to graph this, and then let's see what our variable is. So this value of VI is my x variable in my calculator. When you graph something, that's all you get. You have, if you're putting 0 on this side, and then an x value on this side, where the graph crosses x is equal to 0 is the solution to this, and that's the value in the x direction. Well, this is your x. I'm sorry. When y is equal to 0. Yeah, when y is equal to 0 on this side, we're going to chisel out an x value, and that's going to be our velocity initial. Hell yeah. And then so this does have an angle. It has another variable in here. It's the angle that you chose. And so I just use that as r. You can use theta in the TI-84 calculator, but I'd use just this angle to guess. And what we did is we started here, and so I'm just going to store that as r, because here's kind of the guesses that we did. And so this angle theta is 75.23. The actual answer, using kind of guess and check, came out to be this minus 1.67. This gave us, that angle gave us a value for the velocity initial, the overall velocity of 20 meters per second, which is what this equation also shows. So that's basically how I did this. So I graph, and I can kind of zoom out. Well, yeah, let me get this graphed. All right, hell yeah. So this is our graph, and then I'm going to get a left bound and a right bound. And cool. So at that angle of theta, I get a velocity of 20.051936. And then so what we're going to do is just go one way or another. So if I take this theta plus 1 and store that as alpha r, and then graph this, then I'm going to see if this value for my velocity increased or decreased. And then so it's 20.13. So that's an increase in velocity. That's not what we want. So let's go the other direction, and let's go theta minus 1 and store that as r. And then so this is what I did, so we don't have to do this too much. But then I just, this is a skill I think you should use, because especially for these problems, there's no, it's really difficult to set up multiple problems. Every time you have to graph it and then find a solution. I have not found a way to make that a fast process. Okay, so now we got 0.128008. So that's our solution with, that was theta minus 1. So let's go theta minus 2, store it as alpha r, and let's see if we get even better. And what happened is that, yeah, we were chiseling it down and getting more zeros here. And so this gave us 0.001908, so that was even better. And, okay, so my answer was 1.6, because now let's say I go theta, theta minus 2.1, because if I did theta minus 3, it would be off as well, because that's these over here if you want to follow that. I'm going to store that as r. And then so we did theta minus 2. It's going to be, and that seemed to be better. And then we went theta minus 2.1. And this isn't better. You know what I mean? So we need to go theta. We need to go theta minus like 1.9. And that's what I did. And so you would get this, and you would get that. And so let me just throw in theta minus 1.67. And let's see if that was fairly accurate. And it was converging on, a velocity of 20, which is satisfied by this equation. Cool, and that came out right on 20. I can pull up that answer. We do have a little bit of error there, so but hell yeah. So theta minus 1.67 is this angle of 73.658. That's going to be the angle, and then the velocity initial is going to be 20, and that's the solution. And then so the other thing that I did, and I'll have to double check because it seemed like my equation was wrong. But if I wanted to find where this value was also on the way up, then I want, then for sure, even if this value is right at the top, I still want the lower value. So T2 would be a positive root. And, you know what I mean? I'm kind of done with this problem, but maybe I'll take some time and then... Well, it's kind of fascinating. We can do this. I mean, how hard could it be? All right, hell yeah. Because I also wanted to, yeah, it's good to be able to, like, hey, let's take an equation and then just make a simple modification. It can be the craziest thing because you might make a mistake and then just fall down a rabbit hole of mistakes. But when we subtract T2 minus T1, that first term goes away. And so we just want to know whether we're using the negative or positive root. And that first term, what did we say that first term? That first term was positive. The second term was negative. So we would have positive and then negative. And so if we used the negative... If we use the negative root, we're going to get a bigger number. That's going to be over there. If we use a positive root, we're going to be positive plus a negative, and that's going to be a small. So yeah, so both of these are the positive roots. So I'm just going to go in here. Oh, that's what I did. I think I just put the negative right there. If I put a negative right there, then everything jives, because that turns that positive and that turns that positive. So yeah, I'm glad I figured out what I probably did. So now what we can do though is I'm going to take theta. I'm going to take theta is 30. So I'm going to do 30 stored as r, and then I'm going to put my window like way out. I'm going to do it at 1,000. I think I need to do that, and then graph it. So now what this means is that I'm going to do a really shallow angle, and I'm trying to get to point 1 and 2. You can't even do that though. So let's bring this back down to 100, and I'm going to go, I'm just going to do 60 stored as alpha r. Let's pick something halfway. Oh yes, it's not even finding it. So let's see. What? Oh, you know my window? Yeah, no, window to 100. So let's do 45 stored as alpha r. Graph that. Do we even find a solution for this? So we might have messed up my equation. So let me chill on this for a second. Alright, hell yeah, of course we messed up, because our equation is still t2 minus t1. Even though these are positive roots, I'm still taking t2 minus t1. And so I got rid of that negative out there, because that should be positive anyway. And so we have this t2 as a positive root, but it's got to be minus t1. And so this should work now. And hell yeah, I'm glad that worked. And so we just kind of chose some sort of angle. And cool. And I'm going to choose 30 stored as alpha r. I think I need to make my window 1000. I did this kind of before. Yeah, so if we do an angle of 30, no, I don't even think it'll actually cross. Yeah, that was the thing. Even if I put 2 zeros, that's not going to cross at all. So what happens is if I have an angle that's so shallow, and I go to point 1 and 2, it's going to be way more than 10 meters. There's no way, even if I went a extremely high velocity, it's never going to go through those points with 10. So let's do 40 stored as alpha r, and let's see if that goes through the x-axis. Well, I need to crank down on this. Hell yeah. So if we do 40, if we do an angle of 40, yeah, there's a velocity that will get us there. So now I'm going to find that velocity just using a solver. And that velocity is 60, you know what I mean? So let's see if we can do better. We're going to do 50, an angle of 50, graph that. And yeah, it looks like we're doing better. But still, this is going to get nowhere near that 20, you know. Whoop. So this looks like a velocity of about 30. Okay, 29, not bad. And then so I'm going to go 55 stored as alpha. Well, let's do 60 stored as alpha r, and then graph that. Hell yeah, doing a little bit better. I'm going to go zoom box because we're getting close enough where our answer is going to be, it's got to be bigger than 20, right? And then this is going to get smaller. So hell yeah. So I'm just going to box this in. And so here, and hopefully it'll run faster. Alright, so this value was 22. That didn't seem better at all, but 22.64484. No, that's better than 29. Yeah, obviously. Okay, so now I'm going to go 62 stored as alpha r. Whoop. And then graph that. And then let's see, because I did this. I don't know if I actually put the numbers on this page. I don't think I did. Okay, and that's 21.9. And what we're going to find, I'm going to do 64. You know, if I can, oh, sorry about that. If I can get this to cross, so okay, so it's starting up there. And what I'm going to find is 65. Okay, so that's still crossing. 66. I'm going to get a high enough angle where it's no longer going to cross. So 66 crossed. But 67 probably won't. 60. So an angle of 67. Is there a velocity? No, yeah, 67 worked. Hell yeah. How about 68? If I did a 68 degree, is it even possible? It's not even possible to go through point 1 and 2 and have a distance of 10. You know, the distance is going to be something else. Okay, so that kind of breaks it down. So 67 point... let's just do 67 stored as alpha. Well, 67.1 stored as alpha r. Yeah, nope. So 67 stored as alpha r. Cool. and let's try to pick up on this value. All right, we're going to do a left bound, right bound. All right, booyah. Whoa, bummer. All right. All right, so it's 20.646. I'm actually surprised because I think I messed up the equation on this when I was doing this problem. But, and potentially this also, I don't know, does this also converge at, this is fascinating. Is there, yeah, because this is converging. This is, well, no, that's still 20.64. But maybe, yeah, now I'm confused because I tried to run this where both points were on this side and the distance was 10. So I don't know if my equation is right. I'm sure my equation's right here, and we're using the right roots for the time to be on this side of the equation. I was surprised that that's actually, it's not converging to 20. It's still just a little bit off, but that ain't bad. And so that's kind of interesting. Because if I took this value, this higher value, and then took this distance from 1 to 2, because what we have is like, hey, that, and maybe I'm hitting 0.2 right there. If I hit 0.2 on the way down, the distance would be greater than 10. And so that meant that, hey, maybe I could reduce if I'm trying to hit that point right there. Yeah, that's interesting. And for this problem, I guess I didn't double check to see if, how high the projectile actually gets with a velocity of 20. All right, so, but what we'll do is, let's see, let's box this in. Wait, what do we need to do? Window. Oh yeah, zoom. Zoom box. And we'll box this in. We'll try to get to 20. 20 would be right there. I don't think it's going to approach 20 at all, though. And then we'll do that. So yeah, so if I take 67.1 stored as alpha r, I don't think that actually crosses. No, that did. 68 stored as alpha r does not cross. Oh, that does. But the value of that is still 20.47. So 69 stored as alpha r. And that does not work. 68.1 stored as the angle that we're using. And that's 20.45. So we're still getting better answers, 0.45, but we're just not converging on 20, which would be right there. So 68.5 stored as alpha r, which is our angle that we're using, and that's right there, so that one doesn't work. And 68.4. Okay, so it's not converging at 20. I thought it would be way more off, but for the hitting the 2 points on the way up, it's not. It's fairly close. Which makes me think that you just have a little bit of arc here at the top. So where this point 1 and this point 2 is just kind of slightly arced and just slightly on the way down. It's getting a little bit farther that way, getting that distance, and that's helpful. But this shows that you're really not trying to get up too much higher. Is that what we're... I don't know. Yeah, it's kind of interesting. And what does this also show? Oh, the angle is way smaller. Yes, because what is our angle right here? Our angle is 68.4, and we're converging on a, you know, a halfway solution. Like, obviously, there's a shallow angle where you're just not going to hit point 1 and 2 on the way up. At 69 degrees, you just can't hit point 1 and 2 on the way up. But you can if you steepen your angle, because our answer was this minus 1.67. So our two answers were 73.56 degrees. If we go hella steep, we actually don't, we have to use less velocity, because on the way down we'll hit point 2. If we're trying to hit both points on the way up, we have to, this is our prime angle, 68.4 degrees. And you can't have any higher than that. Where if you're already overtopping on the way up and the way down, you can have a higher angle. You just need more velocity. Where if you do a shallow angle, or if you're trying to hit the projectile on the way down, that's what this equation says. It says, no, on the way up. If you're trying to hit both projectiles on the way up, you can't have a steep angle. Because let's talk about that. If you had a steeper angle, you know, your distance just approaches 6 meters. We talked about how if you went straight up, this one's at 12, this one's at 18, the distance is 6. And so at a certain point, you need, you know, yeah, you need, and if your angle is just slight, in increasing this velocity doesn't help. I mean, it just gets you there faster, making this almost approach 6 as well. If you really reduce this angle to make it a parabolic shape where you're just, you know, you're slowing down and it's taking more time to get to that point. If it takes more time to get to point 2, your velocity this way will carry farther that way. And then so that can increase this. But yes, if you're trying to hit point 1 and 2 on the way up, there is a limitation on the steepness of your angle. Too steep and you're just getting there too fast. Too shallow, also, you can't go through point 1 and 2 without that distance being greater than 10 meters. So that's kind of an interesting thing. And you can pick those out just by adjusting the angle. I call this the mountain climber approach, and maybe I'll come up with a better term. I like that term, mountain climber. You know, it's just kind of, I don't know, it comes off Price is Right, where you get like this many steps for the mountain climber to fall off, and you have to guess, you know, let's say an item costs $22, like right on, and your goal is to be like, hey, you have to guess that item to the dollar. And so you might be like 15. And then the mountain climber will climb 7 steps. And so now you have to figure out if you know, let's say then you did 14. Well, now the mountain climber is going to climb 8 steps. So you have to like underguess and then increase it, but you never know like if you increased it too much. So yeah, so if you did this, if you were like, and maybe there's a way to figure out the exact answer right away, because in this, yeah, that's in this. That's a whole nother video, but that's what it's called, mountain climbing, where you're like, hey, I'm going to try to guess. I guessed high, I guessed low, guess in the middle. But then when you guess in the middle, you don't know where you were. So then you kind of guess one side, it's worse. Okay, go the other direction. It's better. It's better. You know what I mean? But now maybe you don't know where you were. Hey, it's worse. It's better. You know what I mean? So you're just kind of using a guess and check. And it shouldn't take more than like 7 or 8 calculations to really hone in on an answer. All right, hell yeah. So those were my 2 solutions to this. One gave us a spot on 20, which, you know, is reminiscent of this equation. This gives you 20 meters per second. If you're trying to hit both point 1 and 2 on the way up of the arc, then this is your answer, 28.4. And hell yeah. And so that's and that gave us I don't know. I guess we can graph it one more time. It gave us an answer of 20.455, so we're going to leave it at that. Alright, hell yeah, my camera cut out. But yes, if you're trying to hit both points on the way up, it's going to be an angle of 68.4 and 20.455. Now, I don't know how to double check my answers, but or I haven't, you know, so I just do my best, and I use methods that typically kind of double check the answers for you. You know what I mean? It should be obvious if you make mistakes, and that's kind of what I like about, I don't know, using the numerical methods. You know, just kind of guess and check. But we still used solid equations, you know, that get overly complex. So I am looking forward to figuring out, like, hey, how did they simplify this, and the math involved in simplifying. Alright, thanks for joining me. Hell yeah.